All right, we're live. Anybody watch all 18 innings? Nah, right? Nobody's got the time for that. But there was a 14th inning stretch, so they played take me out to the ball game twice in that one, almost three times. So that's amazing. That's really cool. Anyway, so all right, moving on with our lives here. We're back to ANOVA. Okay, so we've done a whole lot of ANOVA now, a lecture and a half up to this point. And today we'll talk about some intricacies of something called post-hoc tests. So additional safeguards that you can take to minimize the rate of type 1 errors. All right, I think the book covers it slightly, but not really completely. So I have a couple of extra slides here for you to know about that. And honestly, I'm not explicitly testing on that on the exam, but it's something that you should know. If I talk about why you would need a post-hoc test when doing multiple comparisons, you should know the basis or the rationale for, the need. What else are we doing today? Yeah, from there, we're going to move on to two-factor ANOVA. Okay, and there's a reading that's up on the Canvas page. I didn't realize that it's been up since I set up the shell, actually, titled two factor ANOVA. It's part of the course resources in the very first tab of Canvas. So I guess I didn't realize that I didn't communicate that to the group. I just kind of left it off saying that I would post it up when in reality it had been up. So that's the issue there. So if you didn't get a chance to see that, bummer, make sure you read it after class and especially before you go into your labs. If you did get a chance to see that, great. Did anybody see that there was a two-factor ANOVA paper already? All right, great. So some of you guys did come across it. Good. All right, so it's not a complete mishap on my end. All right, some people did see it. That's great. Okay, so moving on. So lecture 18, ANOVA continued. Again, the reading for today is supposed to be that additional reading link that's basically connecting you to a website, okay, from Stanford, I think. So make sure you check that out. It's just a website explaining the rationale behind a two-factor ANOVA, talking about the special characteristics of the data and the setup need to have in order for you to perform a two-factor ANOVA. And then also the first bypass that how to interpret a two-factor ANOVA and something called an interaction plot. Obviously, we'll spend most of today talking about that here, but that's additional reading if you haven't read it yet. And hopefully for at least a few of you, that was your primer before coming in. Okay, the reading for Monday is chapter 8.1. So we're moving on to linear regression. All right, we'll start talking about errors, linear regression on Monday. Practice problems for today, I really have none. I would just say use and abuse the internet in terms of coming across more interaction plots and really trying to break down what the factors are doing and seeing if all of the hypothesis or seeing if there's any indication of what the hypothesis might be in the same line of thought that we'll discuss in a couple of slides today. Right, so no explicit practice problems. And again, all those are just suggestions, right? Never really great homework. It's just for you to have something to work on immediately after class. Okay, we have a problem set number 8 and a lab number 7 due Thursday and Friday at traditional times. All right. Yeah. What else I want to say here? We're 2 weeks out from our exam 3. Okay, and those 2 weeks are going to come fast. So basically, let's see, we're looking at the end of the month, right? Halloween's on Friday. This week, then we've got 2 lectures, Monday and Wednesday for linear regression. That's going to cover most of it. All right. And then we have a holiday after that. So not this Monday coming up, but the one after that's a holiday. And then that brings us up to the exam. All right. So we've got 2 more lectures after this on a completely new chapter, chapter 8. So we'll do just linear regression, I guess, or maybe even multiple linear regression, but not logistic regression yet. That comes after chapter 3. Okay. So no pressure, but just be aware. It always creeps up faster than you think. All right. So just putting it out there. So general announcement for everybody. All right. What are we doing here? Yeah, back to the good old ANOVA, right? We got a chance to play around, right? For a day and a half already with this technique, right? Again, developed by Fisher, right? And it's really an analysis of where the variation comes from, right? If it comes from the differences between groups or if it comes, or if there's more variation within the groups, right? That lets you set up a ratio. That ratio you can then look for in a F distribution plot, right? So it's a mass probability function. and you pick that X value of the F ratio and that under the correct distribution plot, given the degrees of freedom, right, that you figure out with the number of groups, and then there's a total degrees of freedom, right? It's a little bit more complicated than we've done before. But at the end of the day, you're basically using your F statistic as a cutoff, right? For which you want to know the area under the curve to the right. All right. And then that gives you a p-value, right? You ideally have an alpha already machinated or thought of, before getting that p-value. And then the beauty of the test is just a comparison between that p-value and that alpha, right? If your p-value is lower than your alpha, then you reject the null hypothesis. And it's the same null hypothesis for all of these regular ANOVAs, right? Just the differences between the groups, it's non-existent as the null, right? So meaning that for the population that sample group represents, the mean for the first group is equal to the population mean of the second group, which is equal to the population mean of the K group, right? K meaning the total number of groups that you have. Okay, so all right, everybody okay with that? And I guess we went pretty deep, right, into how to do this by hand if necessary. Obviously, there's an ANOVA function that you can use, just a standard linear model function in R that you will become very familiar with, I suppose, after this class when you start working on your lab for the week. But we also agreed that we wanted to understand how this works under the hood, right? So again, it's like the analogy I gave is like you should feel comfortable you can change your tire if there was an issue, but when possible, just call AAA. Don't change your tire every time. But anyway, long story short, right? There's two calculations that need to be done independently here, and that's why I encourage the use of this table, right? So you got to calculate the source of variation, right, between the groups, and then the source of variation within the groups, right? The between the group source of variation we ultimately call the MSG, all right? And then the within the groups source of variation we call the MSE. And those are the formulas on how to arrive at both of those calculations. Okay, the F statistic simply the ratio of the MSG divided by the MSE. All right, and then once you have that F statistic, it should all be downhill from there, right? So you have you can calculate a p-value, right, using software or using a table. It's up to you if you want to get really involved with R, if you want to be a little bit more old school. It's completely up to you. Okay. Any questions about the mechanics of this? And I think we went over like 3 or 4 problems, right, on Monday already together. Yes, sir.
Degrees of freedom. So what we go over and try to do.
Yeah. The degrees of freedom for the MSG, right? It's going to be the number of groups minus 1. So if you have a grand number of group comparisons of 3 or 4, let's say 4 groups that you compare. Let's say 5. Let's go back to the explicit example I gave in class, right? The 5 islands of the where we're measuring the beaks of the beak lengths of finches, right? In North Africa. So let's say there's 5 islands, right? That would be your total number of groups. I believe that's K, right? Yeah, K is the total number of groups there. So again, your degrees of freedom for calculating the MSG is going to be the total number of groups. In that particular example, that would be 5 minus 1 or 4. All right. The within groups degrees of freedom is going to be your total number of observations minus your total number of groups. So total number of observations is big N, and that is all of the data points that you have for all of the groups. And obviously, you're going to have more than 2 data points, right, to get an average for each group. So capital N is always going to be larger than K. And whatever that subtraction is going to be the degrees of freedom that you need for your within groups residuals, or MSE, as we broke it down here. Yeah, that should be a wrap for that. Yeah, okay. Everybody okay with that? Any other questions about the mechanics? And again, I'm pretty straightforward with this, right? I definitely did do ANOVAs when I had my entry-level jobs, right? Like being a food quality control technician or working at a food microbiology lab, but it was all done with software. This is, I mean, you're going to do the same thing here in class, but at least once in your life, you should just be comfortable understanding the basic concept of it, right? Which is just the total variation across the groups relative to the within the group's variation, right? And then knowing the basic equation for how to calculate those those two summaries, right? And then just knowing that it's a ratio, and that's all. So I'm usually pretty anti like humans doing too much because that just means errors. But in this case, it seems kind of fun and useful. And again, you're almost guaranteed to use a t-test and or an ANOVA, right, for more than two groups anywhere you work in the future. All right, so definitely not a waste of your time. All right, everybody okay with this? All right, so there's something called a post hoc test. Okay, so often you're going to have this ANOVA give you a significant value, right? Usually you're getting that from software, right? So you're not even looking at box plots even usually, right? It's always advisable to look at box plots to make sure that you have checked the criteria necessary for using that test in the first place, right? So we want to look at the outliers, right? We want to look at the spread of the data. Again, if you do look at the box plots, you get kind of a sense of as to whether or not your null hypothesis is going to be correct or not, but you really shouldn't guess, right? You should just go through with the linear model if you're doing it in R, or with calculating of the F statistic and then getting a p-value if you're doing it by hand. And then at the end of the day, right, you get a certain p-value, right? So that p-value is what the software is summarizing here, right? So the p-value for whatever this comparison was, I guess a total of three groups. It must have been a control group, treatment group 1, and treatment group 2, right? The p-value for assessing the hypothesis of equal population means across those three groups is 6.49 times whatever e to the minus 5. So it's essentially zero, right? So that's going to be a pretty small p-value, right? So again, at that point, you're really unsure as to where the actual differences are, right? You only address the hypothesis, which means that at least one of the population means, right, is very much likely to not be equal to the other population means. As a matter of fact, all the means can be disparate and different from each other, but we just don't know, right? So sometimes you want to know what's going on and do something called a pairwise comparison. All right, but if you just did a pairwise comparison, right? So basically a t-test for each possible permutation of groups, right? Then you're back to this problem, right? Why did we use ANOVA in the first place? That's right, like type 1 error, right? Explosion. So you're back to that. So anyway, if you wanted to do this um pairwise comparisons to actually pinpoint where two groups actually differ a lot, right? And that difference meaning that's probably the cost that's driving an ANOVA or the null hypothesis ANOVA to be um, uh, to not be correct, right? You want to know where the differences are between the groups, right? You can go ahead and do something called a Tukey's significant difference test. Okay, so this is called a post hoc test because it's done after the main test is done, and this is itself a full-on statistical test too. All right, so I won't go into the details. The bottom line is that with this Tukey's on a significant difference test, you end up with an adjusted p-value. All right. And that adjusted p-value ensures it's pretty extreme actually, right? So p-value gets modulated a lot for each one of the pairwise comparison. But that adjusted p-value ensures that you can do this one group against the other, right, for all possible permutations, and come up with a p-value for that specific comparison without inflating your type 1 error rate. All right. So again, you always want to do an ANOVA first. If your ANOVA is significant, meaning that you've got a p-value lower than your alpha, and you know that you expect at least one of the means to be different than the rest of the groups that you're testing in the ANOVA, then a post hoc test or an after the fact test would be this Tukey's on a significant difference, which again has like super corrected adjusted p-values that would then let you pinpoint which groups are truly different from each other. Does that make sense? And again, I think you get to do this in labs. So there's a couple examples that we'll ask you to do this for in the laboratory, but I don't think we'll have the time to like really carry out in the exam. But in the exam, all of the concepts are fair game. So if I were to ask you, right, like what is a post hoc test, right, or select the best definition of a post hoc test from a drop-down menu, hint, hint, you should be able to pick the correct reason why we need a post hoc test, like Tukey's on a significant difference. Everybody okay with that? Yeah. Okay. Another way that you can correct for errors is something called a Bonferroni correction. All right. Was this part of the book too? Is this in your chapter? I think it's briefly mentioned in the book, but not really expanded upon. Okay. So anyway, this Bonferroni correction is a statistical adjustment used to control type 1 errors. All right. Again, in this case, however, instead of adjusting a p-value, we're adjusting an alpha. All right. So yeah, so we're controlling for type 1 errors, that is false positives, when performing multiple comparisons when we use tests such as ANOVA or other tests. There's other tests that involve the comparison of multiple groups. All right. In all of those tests, Bonferroni correction can be used. All right. So again, the difference between the Bonferroni correction and the Tukey's significant difference test is that one is done when all the business is done, right? Like you have to have an ANOVA that's significant, right? And then you're adjusting p-values basically with Tukey on a significant difference, right? With Bonferroni correction, you're adjusting your critical value. So again, you're making it really hard to refute the null with very, very small critical value. Okay. And when having that small critical value, then you suppress the rate at which you would see false positives. All right. So, okay. So it ensures that the overall significance level alpha across all the tests remains within the desired confidence threshold. Okay. So again, the purpose here is when performing multiple pairwise comparisons, for example, ANOVA, the likelihood of finding at least one significant result by random chance increases. The Bonferroni correction adjusts the significance threshold to maintain the overall type 1 error. And the correction is quite simple. It's actually you change your alpha. Say that your original alpha is 0.05. You would then change that alpha to something called alpha star, okay? And alpha star is your original alpha divided by m. And m is the, let's see, m is equal to the number of total comparisons that can be performed. All right, so I have the general formula for that there. M for k groups, right, that you're comparing would be 1/2 times k minus 1. And that applies for any number of groups. So if you have 5, it's basically 5 times 5 minus 1, or 4 divided by 2. Okay. Everybody okay with that? So again, this type 1 error thing's pretty real, right? Every time you do a comparison, right, or you do a series of comparisons, you're increasing the chances that you're gonna have false positives. All right, so there's a lot of things to be done about that. The first thing to be done is to use ANOVA to figure out if, like, out of 100 groups, there's at least one different one. So that's pretty straightforward. ANOVA is the first step. All right, if you want to know which two groups differ the most or where the major differences are, you would do a Tukey on a significant difference test. All right, and if you want to be extra careful, you can adjust your alpha before doing anything to lower it to the point where you make it really, really hard to generate false positives. And that would be your Bonferroni correction. So again, yeah, summary to that, that's what I just said. I always keep speaking like one slide ahead. All right, Bonferroni correction is a multiple comparison adjustment. All right, and the purpose is to control the overall type 1 error rate across multiple tests. And what it does is a significance threshold adjustment, right? Again, significance threshold means alpha, right? That's your critical value. Okay. Post hoc tests would be Tukey's on a significant difference. There's many other tests too. Obviously, we're not going to cover them all. We barely cover one. And this is, again, a whole nother monster. It's like the whole enchilada. It's a whole nother test with its own set of assumptions. All right, I'm just kind of being practical about it here. But what the Bonferroni test will do is do a pairwise comparison, okay, and identify which groups truly differ from one another after you've had a significant ANOVA result, okay? And again, it's doing this by adjusting the p-value. All right, any questions so far? Bonferroni, yeah, you can do both. Yeah, you can double up and correct the alpha and do a post hoc test like Tukey on a significant difference. Yeah. So yeah, it's like order of operations, right? Yeah. Anybody else? Any other questions? All right. So it's this are pretty classic post hoc test, especially Tukey's on a significant difference. Every time I report an ANOVA, I just automatically on my line of code always put a two keys correction for sure. Yeah. All right. Let's have a look at these conceptual questions real quick. Give you guys a few seconds to think about it. True or false? We're going to play a game. Binary game, I guess. Determine if the following statements are true or false, and explain your reasoning for statements you identify as false. It's funny. All right. Explain your reason for statements you identify as true too. Okay. So if the null hypothesis that the means of four groups are all the same is rejected using ANOVA at a 5% significance level, then A, we can then conclude that all the means are different from one another. True or false? B, the standardized variability between the groups is higher than the standardized variability within the groups. True or false? C, the pairwise analysis will identify at least one pair of means that are significantly different. True or false? D, the appropriate alpha to be used in a pairwise comparison is 0.05 divided by 4, which is equal to 0.0125 since there are four groups. True or false? Take about a minute to think about this. All right. Do you guys have the PDF? Yeah. All right. Don't go to the other PDF, please. Stay on this slide. All right. Let's talk about A. Can we conclude that all the means are different from one another? True or false? False, right? It's um it's not what the null hypothesis is testing, right? The null hypothesis is pretty specific, and it's just that all of the means are equal, right? And one of or like the immediate the simplest alternative to that hypothesis would be that all of the means minus one are equal, that there's just one that's different. And so yeah, this first statement is extremely unlikely. Everybody okay with that? Yeah. Okay, so we would say that's false, right? All right, B, the standardized variability between groups is higher than the standardized variability within groups. What do we think about that? Anyone else? Please don't go to the next slide. Play this game, play my binary game. Anybody? Definitely true, right? As far as I might be wrong, but I feel like that's the only true one here, honestly, right? There's nothing else, right? If nothing else, you should know that that's all the ANOVA is, right? You're standardizing variability, right, between the groups and comparing that to the standardized variability within the groups. And that's your F statistic. Yeah. So again, and that's exactly what happened here, right? We got an F statistic that let us reject the null hypothesis, but we don't know how close we were to not being at not being below 0.05, right? So again, all that we can really say at the end of the day is that when we standardize variability within and between groups, that our F statistic, it's slightly greater than one. Everybody okay with that? All right, so the next one. The pairwise analysis will identify at least one pair of means that are significantly different. How do we feel about that? True statement or false statement? At least one of the means will be different. Don't be shy. It's binary. Yes. Sorry, we got a yes here. Anybody else? Maybe, no, what?
Assuming because you reject the null, that means there's at least one that's different. So you have to assume there's at least one pair that's different.
That's a fair assumption. That's a fair assumption, but this is the not the pitfall, but this is a limitation of ANOVA. Again, when even if under certain conditions, right, you're just going to need to tip over an F value of 1, right, to like have more variability between the groups and within the groups. Tip over that to arrive at a p-value that's actually lower than an alpha, even if it's an alpha of 0.05. All right. But that may still not translate into a single comparison being discernible from the rest of the comparisons. I know, it's such a letdown, right? Like we're so excited about this test, and then I tell you this, but do not despair, right? Like that is what happens sometimes. Okay. The collective difference, right, in variance from within groups and the collective difference of variance between the groups, right? Or not just collective and standardized, right? Is compared to generate this F statistic. And again, under certain conditions, right? That comparison may not be that extreme, but still fall under alpha. And when that happens, you've rejected the null, okay? But when you do the pairwise comparison, you may not have a comparison that's actually significantly different.
Well,
That's right. Yeah. So you can, when that happens, right, you can, at a risk of a type 2 error, right, adjust the alpha, right, and then see how much of an adjustment is needed. Or otherwise, you would just be in a weird situation where there's, I mean, I do have that situation drawn in one of my examples, right, where you've got a very near 1 value that I say is a situation that's extremely uninformative, actually. Okay, and again, that extremely uninformative situation, right, can have variation within itself. And that variation can lead to a situation where you're rejecting the null, and theoretically, one of the means should be different than the rest, but then you can't detect it. All right, extremely rare. All right, but I've seen it happen once with my data. It's actually true that this situation emerges once in my data. All right, and again, every one of my research papers usually has an ANOVA, and it hasn't happened any other time except for once. All right. So it's when looking for iron oxidizing bacteria across 6 different substrate types of different geological or different mineralogical compositions of rocks at the bottom of the ocean. It happened to me. But all right. So everybody okay with that? So again, be aware of that. All right. Just because you have a p-value that turns out to be lower than a certain alpha, it doesn't mean that you'll always identify a single comparison that's truly different across your groups. But the net variation between and within the groups, right, is is um uh is an F statistic that's higher than 1 at least. Okay. Everybody okay with that? I know that's the worst part. Like we try so hard for ANOVA and then like well, it's not perfect. Nothing is perfect, but keep that in mind, please. All right, final point here. The appropriate alpha to be used for in a pairwise comparison is 0.04 divided by 4. I guess they told us we have 4 groups here, since there are 4 groups. Is that true? What would be the appropriate alpha to be used? It is K times K minus 1 divided by 2, right? So that would put us at 6 for K, no, 6 for M. So alpha star would be 0.05 divided by 6, which is not that. All right, everybody okay with that? All right, any questions about like the higher level, like forest level view conceptual questions of ANOVA and interpretation? Okay, well, that's going to be a wrap for the regular ANOVA. All right, we're going to move on to a two-factor ANOVA now. Obviously, you can check out the answers there. All right. All right. So far, right, we've explored one hypothesis only. All right. The one hypothesis that we've explored is that the population mean for all the groups is equal, basically. All right. So that's what we've been working with our regular ANOVA. Okay. Now we're going to step into this two-factor ANOVA territory. All right. And let me just start off by telling you what this data looked like. All right. With ANOVA, you have a single factor, right? For example, islands, right? That has multiple levels within it, right? The level of islands was Tenerife, El Hierro, all of the 5 islands, right? And all of those levels are associated with a single numerical observation, right? And that numerical observation would be the length of the beaks of a finch, right? In the last example from Monday. In this case, we've got two factors that are associated with every numerical observation. All right. So again, in this case, we've got diet and exercise, right? Collected for a single individual that had their triglycerides measured. Everybody okay with that? So again, there's one numerical value, right? 98 at the very top, right? Last column of the first row. And that 98 is part of two groups, right? The two groups that that 98 is part of is diet and exercise. All right. The diet group has two levels. So in that group, right, or for that factor, 98 can either be good or poor. All right. That factor is diet. Whoever's got that triglyceride level either had a good or bad diet. All right. At the same time, whoever's got that triglyceride level either exercise with high frequency or exercise with low frequency. All right. So again, all right. So now again, like I said, we're moving in. We're going to be able to ask some new hypotheses, new and exciting hypotheses that we've never asked before. Right off the bat, we're basically doing carbon copy hypothesis of what we've done before for each one of the factors. All right. So if we just took diet, right, that's a t-test, right? Or pretend that it had more than 3 levels, it would be an ANOVA, right? If diet was good, poor, or intermediate, that would be an ANOVA, right? So there would be a mean for good, a mean for intermediate, and a mean for bad, okay? Or I guess not bad, poor, yeah. Everybody get that? So it would be 3 means, and we could compare if there's a difference between the levels with the ANOVA, right? Which is exactly what we've been doing with the islands and everything else, all right? Ignoring diet and just looking at exercise. Again, we have high, low, and let's pretend that we have intermediate. That would be another ANOVA, right? So in this two-factor ANOVA business, we're actually going after 3 hypotheses. I just explained the first 2 out of the first 3. The first one is just a regular ANOVA for something called the main effects of the factor number 1. Let's say it's diet, all right? Are the means for the population groups that comprise the levels of that factor the same all across, right? That would be the null hypothesis. Same exact null hypothesis for the other factor, exercise. All right. So that's 2 out of our 3 hypotheses now when we do a two-factor ANOVA. Our third hypothesis would be something called an interaction effect. Jeez, I just saw a golden eagle fly right across right behind. That was awesome. Yeah. So our third hypothesis would be something called an interaction effect. And that hypothesis would test whether or not the outcome of diet is influenced by different levels of exercise, and vice versa, if the outcome of exercise is influenced differently at different levels of diet. All right, so we'll get to that. So that would be an interaction. And that hypothesis is, I guess, officially stated as an additive effect. So yeah, like whether or not factors are additive. All right. So obviously I got the next half an hour to talk about that. Okay. So just bear with me. All right, so let's go ahead and read through the summary real quick. So again, two-factor ANOVA, right? Or factorial ANOVA, those names are interchangeable. I just talked about what that data looked like, right? So you have single numerical values, right, that are attached to multiple levels of at least 2 factors. All right. Level 1 here is diet. Sorry, factor 1 here is diet. And as I have it written, it's got 2 levels, right? Good and poor. Factor 2 here is exercise. And as I have it written here, that exercise got 2 levels, high and low. Okay, so all right, you're going to have 2 independent variables or factors. A two-way ANOVA includes 2 categorical independent variables known as factors. All right, so those are basically our column headers, right? Diet and exercise here. Each factor has 2 or more levels, that is, groups or categories that define the different conditions or categories for the analysis. Everybody okay with that? Again, our 2 factors here each have 2 levels as I wrote them, right? Then I came up with my hypothetical example that maybe there was good, intermediate, and poor, and high, intermediate, and low. Then these 2 factors would then have 3 levels each. All right, so they can have multiple levels, but it has to be 2 factors. All right. Another component here of the data frame is that we have a dependent variable, right? So we're assuming that the level of the factors affects this numerical outcome, right? That's the assumption here. That makes triglycerides, right, our numerical outcome, the dependent variable, right? So the dependent variable must be continuous. That's super important. It always has to be continuous. It should be normally distributed within each group, defined by the combination of factor levels. Okay. This variable is what the test aims to analyze to determine if different levels of the factors have significant effects on it. All right. It's basically our source of variability, right? All right, number three, main effects. The two-way ANOVA examines the main effects of each categorical independent variable on the dependent variable separately. All right, so again, the main effects is, I guess, more or less equivalent to an ANOVA for one factor at a time. All right, where like each level of that factor is a group of the ANOVA. Does that make sense? So, yeah, main effect of factor A. This assesses whether there are significant differences in the dependent variable across the levels of the first dependent variable. Again, kind of an ANOVA, right? Just what we've been doing. And it's the exact same thing for the main effect of factor B. That would examine whether there are significant differences in the dependent variable across the levels of the second independent variable, right? But I guess I'm considering the levels as groups. Okay. Everybody okay with that? All right. On to the exciting part. Point number 4 here, the interaction effect. Does the effect of one independent factor on the dependent variable depend on the other independent factor? Is the interaction term. All right. And again, that's a hypothesis that we've never examined before. All right. So again, all of these two-factor ANOVAs, well, first of all, they're kind of figured out using software. All right. The only thing you're doing by hand here is putting together something called an interaction plot that allows you to explore a little bit ahead of time from the software this interaction effect, all right, that we'll discuss in more detail. But in the meantime, let's look at another example of data. All right, so these are mealworms, right? So these guys become beetles, really cool looking beetles. Anyway, so what we've got here, right, is weights of the pupa for this mealworms in milligrams. All right, so numerical continuous data, right? And each one of those observations, right? So each one of those individuals is categorized by sex and by the type of media they consume or their food. Okay, so you've got a two-factor setup here. Everybody okay with that? All right, can someone name off one of the factors? Type of flour media. How many levels in that factor? 3 levels. And the other factor? And how many levels in that one? Exactly. So, all right, everybody sees this as a perfect setup for a two-way ANOVA now, right? Numerical data attached to two factors, and each one of those factors has at least 2 levels, right? In this case, type of flour media factor has 3 levels. Sex has 2 levels, so we fit all the criteria. All right, everybody okay with that? All right, so cool. All right, so I guess we've broken down, right? We're basically generating groups. That's what we're doing here. All right. Uh, what's this? Okay, yeah. Numerical response is the weight of the beetle, right? Whatever this pupa was. Factor A would be flour, kind of arbitrarily picking the factors. Once you pick one, just stick to it. Okay. It can be the other way around too. Factor B would be sex, right? And then when we tabulate the data in this way, we basically generate groups from which we can derive averages. Everybody okay with that? So in this case, we've got a total of 6 groups, right? And I'm highlighting here specifically a group that pertains, right, to 2 specific levels of each factor. All right. This group is male level for the factor of sex, and it is wheat flour level for the factor of media type. All right. So that every one of these groups is basically an intersectional group of different levels of the 2 factors. All right. Are there differences between the diets? Can you guys eyeball that? Anyway, that's a loaded question, right? Because if somebody asked me that, I'll ask, do you want me to consider sex or not? Right? If you don't want me to consider sex, and I've got 6 observations that I can that I can arrange at random, right, and come up with the same average, right, every time. Um, and then I'll have three averages, and I can run an ANOVA, right? This wouldn't be a two-factor ANOVA. That would just be an ANOVA, right? If sex is going to be a consideration here, then you can no longer just randomize the data in the column, right? You have to order it. And that ordering, right, is going to be based on female and male, which are the two levels of sex, biological sex, at least for these animals in this case, Okay. So yeah, so not that straightforward anymore, right? We've got another level to worry about in a two-factor ANOVA. So are there differences between the sexes? Same issue, right? So again, if media type is to be considered, right, then we don't have nine observations for like female and nine observations for male, right? Those observations get pared down to the observations associated with each particular media group, right? So again, everybody see the major differences here. There's um, the splitting of how you group things that we didn't consider with regular ANOVA because we only had one factor, right, which was an island, and then the identity of the island, right, being the single level there. All right. Okay. Here's the third question, right? That again, I said this is a brand new question that we never really asked before. Does flower type affect female beetles differently than male beetles? Everybody see how that's a completely new question now. And could that even be possible? In many situations in biology, there is interactions between groupings. All right. And this is why this is so useful here. Yeah, that's definitely true. All right. Yeah. Question.
In one factor, that's the other one, the other factor.
In this case, right, we got to ground it biologically. And the way that I phrase it right there is the only possible way that it would make sense biologically, right? So whatever my combination of female to male ratio is in my experiment, right, shouldn't affect uh shouldn't affect my choice of feeding wheat, corn, or oat, right? So that wouldn't make any sense. I think that logically will break down going in that direction, but in the other direction makes perfect sense, right? Like there could be a difference in the numerical response variable, right? Which is weight of the beetle um, as a function of what I'm feeding across the two levels of sex factor. Okay. So that's a great question, actually. It seems obvious, but it's not, actually. There's some situations where it'll be more gray, but here I think it's pretty straightforward. All right. Anybody else? All right, so let's look into this groupings a little more carefully now. And by the way, you're gonna for the lab, as you'll see, you'll just get tabulated data that looks like this, like multiple columns and rows, right? Or actually just columns with one column being your dependent variable, just like we had here, like that, right? And then the other two columns being factors with different levels. So that's what that's going to look like. And then you just input that onto R, and then there's a function that gives you the output. And I'll show you what that output looks like, but I'm kind of rambling. At this point, what we want to do is try to wrap our minds around this interaction effect. All right. And to do that, we'll start setting up something called an interaction plot. All right. So again, once you break down the data like I did here, what you're basically looking at is intersectional groups. All right. And you can come up with means for all the intersectional groups. And it's super useful to plot this means in like an XY axis and see how those groups change as a function of levels of different factors. All right. So that will give us a first hint as to whether or not there's an interaction. All right. But again, as with the ANOVA and like eyeballing things with the box plot, right? You don't want to go by your eyeballing of the interaction plot. It's super interesting to put together and it helps you really rationalize what's happening. You really want to go by the actual output of the linear model on your computer. Does that make sense? So again, it's fun to think about and rationalize, but you don't want to say that there will be an interaction based on what your interaction plot looks like and not do the test. You always want to do the test. All right. Anyway, All right, so setting up an interaction plot. All right, so all we've got to do to set up an interaction plot is just plot the intersectional means. All right, and again, I pretty much described what an intersectionality was here, right? It's just the groupings that are made when separating, right, data into factors and levels of those factors. So again, factor A in this case has a total of 3 levels, alpha 3. All right, factor B in this case has a total of 2 levels, B2. All right. The intersectional groups are the means for the I level of factor A and the Jth level of factor B. All right. So that's just matrix notation. All right. You're either familiar with that or you're not. I guess if you're not familiar, listen on. If you are familiar, this is old news, right? So again, I color coded the different groups here. All right. That I'm annotating the mean for it using this type of matrix notation. Okay, so again, the ith group for factor A in this case is level 2 of factor A. Level 2 of factor A, if I start with wheat, would be 1, 2, and 3. Level 2 of factor A is corn. All right. The jth group for factor B would be 2 in this case. All right. And level 2 for factor B, if I start with female and then go to male, would be male. So I'm basically at the second column, second row of this intersectional table. Does that make sense? And this will be a mean, right? I guess kind of a sample mean, but we'll use this sample mean to then test test the main effects, right? Meaning that all the population means would be the same. All right, everybody okay with that? Okay, the intersection or the way you would write that using that notation for this intersectional group of corn and female would be the mean for that group being 2 and 1. Everybody all right with that second level of factor A, first level of factor B? All right, so on and so forth. One final example here. So this bottom corner intersectional group in green would be the third level of factor 1 and the second level of factor 2. All right, so males eating oat. All right, note that you can also do this. So this would be the mean for corn. All right, so again, this first position is the level of factor A. All right, factor A is diet. I'm saying the second level for factor A independently. That's what that little star is. That usually means a wildcard when you use Unix in the computer. And wildcard means that you can substitute any keyboard character there. All right, so that means any number basically for the second factor. So this means this mean here will represent all of these values added up independently of whether they come from females or males. So again, that would be mu2 star or wildcard, however you call the star. No, it's not even a star, right? It's an asterisk. Yeah, okay. And again, that would be, again, the mean for all corn values independently of the levels of the second value, independently of whether they came from a female or a male, okay? Yeah, independent of sex. Conversely, right, you can also have this, or similarly, you can have this, you can have any level of flour, right, any level of diet, but you just want the mean for just the females, right? So it would be all of these data across all of the diets, right? So just the first level of factor 2, and you get a mean for that. And that would be, again, the mean for females independently of diet. Just giving you a sense of the notation there. Is that okay? Yeah, so I think that the reading that I give out talks more about this. You'll see more of that in the lab. So it's not just my chicken scratch thing here. It's just to guide you into what you're going to see in other materials they have available. All right, everybody okay with that? All right, moving on. So anyway, this is how we would visualize that data set right there. All right, so these are the actual means, all right, plotted for every one of those intersectional groups. All right, so the mean for female corn and the mean for male corn are both right here. All right, they're basically right on top of each other. Does that make sense? Female corn and male corn. Yeah, they're pretty darn close, right? So each one of those points, when plotted with flour as the x-axis and then different colored lines as the different levels of the second the second factor, they very much overlap, right? So they almost have the same mean. Everybody see that? All right, so if we then plot, right, the mean for male oats and the mean for female oats, we see that there's a difference there, right? And we'll get back to interpreting that accurately, but that difference is not the same, right? So what happens when we feed oats to females relative to males? Females grow more on average and males grow less. So it's basically a differential outcome, right? In terms of the magnitude of the outcome, right? Again, if they're the same at corn and then they're different at oat, but they're a different, right? The males are smaller than the females, right? Then that means that there's an effect of flour on the numerical response variable, right? For the different sexes. Everybody okay with that? All right, so let's go to the next step over, right? If we feed wheat to both of them, to both females and males, right? What happens? Right. So yeah, so I guess if you just consider oat to wheat, right, you wouldn't be able to see an interaction there because there's no different outcome there, right? The outcome is the same for both levels of sex, right? And that similar outcome is just higher growth in wheat relative to oat. Everybody okay with that? So again, if we just consider two factors of diet here, just oat and wheat, there wouldn't appear to be an interaction, right? But the fact that when going from corn to oat, right, there's a differential effect on the values for a dependent variable, probably indicates that there's an interaction here. All right. All right. Yeah. So I mean, I don't know the biology of these beetles or whatever, but there must be something in oat that's missing, right? That the males cannot generate, but that the females can. Does that make sense? So again, the net increase might be just more caloric nutrition or whatever when eating oat relative to corn. That's probably true, right? Corn's a very fast, starchy carbohydrate that burns pretty fast compared to oat, right? So there's probably more energy, either through direct metabolism or through indirect fermentation with the microbiome of the gut of these animals, right? Yeah, but that oat, right, that change in diet is negatively affecting males relative to females, right? So again, we went across one level of one factor, right? Corn to oat, two different levels of diet, and got two different responses as a function of which level of the other factor, male or female, we were looking at. Everybody okay with that? Yeah. So factor A, again, diet, factor B, female. All right, anyway, all right. With this two-factor ANOVA business, like I've been talking about now for a couple minutes, you've got three hypotheses. All right. The first hypothesis is that all groups of factor A have the same mean. All right. So again, that's more or less standalone ANOVA, right? For factor A, with like the levels being different groups. The second hypothesis is that all groups for factor B have the same mean, same thing for the other factor. The third hypothesis would be that the impact of moving across factors is additive. All right, so I'll cycle back to talk about that a little more in just a second. Let's look at another data set here. What do I want to say here? Okay, let's look at what this data frame that we just looked at a second ago with the pupa weight would look like when you run it through R. All right, so this is all you have to do. You'll learn how to do this in the lab. All right, just read this .csv, you read it into R, and then you run this. You run a linear model or an ANOVA test directly, and then you print the results. All right, then you're basically tasked with interpreting the results. All right, this is what the results would look like here. So again, here we've got an R output for an ANOVA table. All right. The columns are clearly labeled as they will be on R when you print this out on your computer, right? You have your sources of variation, degrees of freedom, sums of square, means of square, F statistic, and your p-value. All right. So that diet, right, is literally our factor A, right? And that p-value is the p-value to assess the hypothesis of equal means across the levels of factor A. Are we rejecting or not rejecting? Rejecting the null, right? Next, sex is literally your factor B. That next p-value is addressing the hypothesis of equal means across the levels of factor B. In this case, female and male, right, for sex. Reject it, right? That third one there, with the two dots connecting them, is your interaction term. So that is your interaction hypothesis, all right? Whether or not the outcome, right, the response variable is affected by which levels of which factors you're comparing, all right? So that's basically what you're testing there. Are we rejecting that null hypothesis? Is there not an interaction? If things are additive, that means that there's not an interaction. And that's the null hypothesis, that there isn't an interaction, all right? So what are we seeing here? We reject. Yeah, so they're all three of them are rejected. So what we can say is that at least for this pupa weight as a function of sex and diet type, all right, which type of flower you feed this pupa, we get the following result. All right, our first hypothesis is rejected, right? So we must conclude that there is a difference between at least one pair of diets. All right. Our second hypothesis is also rejected, which means that we must conclude that there is a difference between the sexes. All right. That's our second null hypothesis rejected. Our third hypothesis is rejected. And again, we conclude that there's probably an interaction between diet and sex across at least one combination of the levels of those two factors, which is what we saw there too, right? Everybody okay with that? All right, so here's an additional exploration of what this interaction plots may tell you. Okay, so you want to do the same thing every time you approach this interaction plots, all right? You want to ID the factors and levels, right? So just be very comfortable. They understand what it is that you're looking at. All right, you want to note the trends within factors for each level for main effects. All right, and you want to note the trends across factors for potential interactions. All right, so let's just have a look at this. All right, so this is a trait measure. Let's call this weight again, all right, for like pupa or whatever, species A, species B of pupa rather than male and female, all right, across environment 1 and environment 2. Environment 1 may be high arsenic, environment 2 may be normal, no arsenic, right? Thus, independently, all right, independently of which environment you're looking at, all right, does the weight change across species? Well, slightly, right? Or I would say that the average, right? I would say that on average, like almost not, I think you're being like super precise and yeah, one slightly above the other, but more or less, right? There is no change, right? Species A is staying flat across environment 1 and environment 2. And species 2 is staying flat across environment 1 and environment 2, right? Everybody see that? Yeah. And then if we completely ignored species and just took all of the data for environment 1 and environment 2, independently of the color of those data points, right? The average would be the same across both environments too, right? So there's no net significant effect. There's no significant effect at all across species or across environments here. So whatever it is that we're measuring here, if it's the weight of pupa or whatever, is not being affected by the environment in which we're collecting them. And it's also not affected by which subspecies of beetle they actually belong to. Everybody okay with that? All right, let's move on here. So let's look at a species effect now. So in this environment, right, we see a significant difference between members of species B. This dot, by the way, represents an average, all right, of like all the observations that we have for species B. That's what that represents, right? So we're talking about intersectional groups. It's not just a single observation. It is a mean that we're plotting here. All right, so there's a bunch of blue dots, but that's the mean for all the blue dots, all right? And then we've got a bunch of red dots, but that's the mean for all the red dots, right? So here, right, if we were to just ignore the color of the dots, all right, you would have a bunch of red ones up here and a bunch of blue ones down here, whose averages are we're seeing there, all right? But then we ignore their color. They all become black, all right? The average weight for all of the observations, irrespective of species, we don't have species anymore, will probably be in between these two in environment one, right? And it will probably be in between these two in environment two, which means that there will be no change across environments. Everybody see that? Again, we're plotting the mean here. So let me reemphasize that. That red dot represents the mean for a bunch of other red dots that are around, maybe 6 or 7 more observations. The blue dot represents the mean for a bunch of other blue dots that are lower than the red dots. And if we ignore species, it means that those colors go away and they all become black. And if they all become black for both the environment one column and the environment two column, it's more or less the same average. So nothing changes across environments, right? The average would be here for environment one, the average would be there for environment one, independent of color. Everybody okay with that? So that there would not be again an environmental effect here, right? All right, so let's consider species again now, right? There's definitely a difference, right, across species for both environment types once we consider the colors again. So this would be a net species effect. Everybody all right with that? Again, let me hear your thoughts, huh? This is way too far-fetched. Let me know. Okay, let's look at an environment effect now, right? So here, the difference, right, of the averages independent of species does change across environments. Everybody okay with that? So again, this red dot, right, has a ton of other red dots around it that coalesce into that red dot average that we're seeing. The blue dot has a ton of other blue dots around it that coalesce into the blue dot average that we're seeing. But guess what? Both of those averages are literally on top of each other. So there's actually no difference between species type, all right, across either environmental observation, right? The same thing's happening in environment two. There will be no difference between the red cluster of dots and the blue cluster of dots that we're representing with single mean dots here, okay? But if we then ignore species completely, right, and then looked at the averages there, all right, and looked at those averages across environment, there's obviously a lower mean, right, for the combined red and blue dots that make up these averages in environment one than there is in environment two. So again, there you would not have a species effect. You would have an environment effect, right? So the environment is triggering changes in the averages of your dependent variable, not the species. Everybody cool with that? All right, so look at this other, the final plot here, the final plot of the day. So here you've got, you have different values, all right, of your dependent variable for each species, right, across each environment, all right? Interestingly, if you average those out, right, like the average of all the red and blue dots would be there, and the average of all the red and blue dots would be here. So there will be no difference of values independent of species across the environment, right? But which species are high in value, right, and which species are low switches as a function of environment. So again, just that overlap of lines kind of gives away the fact that there's going to be an interaction here. All right, because that means that the directionality of the effect is changing. And that is your interpretation of whether or not there's an interaction in one of these interaction plots. All right, everybody okay with that? All right, I think that we'll leave it at that for today. All right, I've got a couple more examples, but we'll go over them next time, I think. Okay, I'll let you give it a shot on your own. And for those of you that didn't do the reading on the two-factor ANOVA, please try that reading. That should tee us up to basically revise these other examples that I have here and maybe examples in the reading that I assign so we can continue this conversation fresh on Monday, all right, for the first 10 minutes of class. before moving on to our next chapter, which is going to be linear regression. Everybody okay with that? All right, so yeah, that's enough. Yeah, we're done. Have a good rest of your day, everyone.